Example 3, related rates. In this example, we're going to take a look at a cone that has water in it. So the cone has a radius of 2 centimeters, a height of 8 centimeters. And the question is, how fast is the water dropping when the height of the water inside the cone is 6 centimeters? Now notice the water is coming out of the bottom of the cone at 0.02 liters per minute. Few things we're going to have to do in this situation. We're going to have to come up with some equations, and one real important aspect on a situation like this, make sure the units of what we're dealing with match. So, first of all, notice my measurements of my cone are in centimeters, but the rate at which the water is flowing out is in liters per minute. Little thing you should remember, just to start with, is 1 liter equals 1,000 centimeters cubed. So, to go from 0.02 liters to centimeters, because that's the unit that my measurements are in, I simply multiply by 1,000. That means this rate is 20 centimeters cubed per minute, is the same as 0.2 liters per minute. That's a very important thing to start off with, is make sure my units all match. So, I'm going to make this a little smaller and come up with some formulas. Again, these set of formulas can come up from two things. In blue, I've got a radius and a height, and in green, I have a radius and a height. I like to talk about the difference. The green values are static, which means they're not changing. So the green will always be 2 centimeters of a radius. Its height will be exactly 8 centimeters because that's the cone itself. Where in blue, the height of the water is changing, and as the height of the water goes down, the radius at that level of water will also be changing. So basically a cone inside of a cone. So I'm interested in the volume of the water equals, inside of a cone, pi over 3r squared times height. And we're interested in how fast the water is dropping. So what I'm really interested in is, what is that change in height with respect to time? How fast is the water level dropping? Now, again, I have too many variables, and every time you have too many variables, you're going to have to attempt to do a substitution. So, how are we going to do that? Again, in this case, we might want to notice something. That if I call this angle here theta, then the tangent of theta, I'm just going to write that over here. The tangent of theta would equal r over h. However, the cone itself would have the same theta inside of it, so it would equal 2 over 8. So you're going to be using either a lot of similar triangles or trigonometric relationships, sine, cosine, tangent, cotangent. All of those are good relationships when you have triangles involved. And now, since I'm looking for the change in height with respect to time, then I'd like to get rid of my radius. So I'm going to solve for r. And 2 over 8 is going to reduce to 1/4 h. And at this point, I'm going to plug that into my formula. Volume equals pi over 3 times r. Oh, not r. R is 1/4 h squared times h. I'm going to simplify my formula. Volume equals, when I square 1/4, I get 16 times 3 is 48. And h squared times h is h cubed. So if I wanted to, I could solve for h at this time, but I really don't have to yet. But you could if you wanted to. I'm not going to. Why? Because I can use the technique of implicit differentiation, and if I take the derivative of this now with respect to time, that's minutes, I will get the change in volume with respect to time in minutes, actually dt, is going to equal 3 times pi over 48 h squared, so I'm just using my power rule, times dh dt. And at this point, I can plug in dV is my change in volume, which we know to be 20 centimeters cubed per minute. 3 and 48 reduced to 1/16. H is my height at that moment, and we already knew we were talking when the height was 6 centimeters and dropping. Times dH dt. Oh, one little thing, my volume is actually decreasing, so since it's going out, we should express it as a negative value. Okay, it's just a matter of simplifying this a little bit. So we've got what? 36 divided by 16. You might want to reduce that fraction to 9/4. And now it's just a matter of cross multiplying. So 4 times 20 is negative 80 over 9 pi equals dH dt. And we might want to get a decimal approximation of that. So negative 80 divided by, make sure you put it in parentheses, what do we have here? 9 pi. So my height is dropping at almost 3 centimeters per second. We'll round it to the 100th place for this particular example. So negative 2.83 approximately. 2.83 centimeters per minute. I'm sorry, not second. And again, just to recap a little bit, I had too many variables in my initial formula. I was able to use a trigonomic identity to come up with an equation that allowed me to do a substitution. That substitution allowed me to relate the two variables, volume and height, alone, so that when I took the derivative, the rates in change of the volume was then related to the rate of change in the height. And it was just a matter of solving and plugging in the location at that point.